So in this section, we start by looking at the domain and the range of a function. And especially we're going to want to find the domain and the range when we're given a formula for the function. But let's start by understanding what we mean by the domain and the range. And one good way of thinking about the domain and the range is really well explained actually in the books. I just copied it down. Then they say on page 180 that we can visualize the domain as a holding area that contains raw materials for a function machine. So we have to think of a function as something that's creating something out of raw material. Okay, so we're feeding the raw material into the machine. So the machine that I've called F for function is right in the center, and we feed it so that you can see the little red arrow showing how the raw material enters the function machine. So we feed that raw material into the function, and then it creates some output in another holding area that's called the range, and those outputs are the function values of whatever we feed into the machine. So we could think like if you feed x1 that's in the domain into the machine, comes out y1. If we feed x2, comes out y2, and so on. Okay, so what we can feed into the machine is the domain. What we can get from the machine is the range. So first example, find the domain and the range of this function. Okay, so what we have to look at are the things that we can feed into the function. So it's pretty easy to find what the domain is. You just have to collect the numbers that are linked to other numbers in the right hand column. So 0 is actually not associated with any of the numbers in the right hand column, so we can't feed 0 into that machine, at least from the information we have. They're telling us we can't, so 0 is not going to be part of the domain. But 2, we can feed it into the machine and get out 10 from it. So 2 is going to be in the domain, as you can see, 3, 4, 5, and 6. And the range is what can possibly come out of the function machine. So 10, 20, 25, and 40. Notice how I'm using braces for to surround the elements of the set. So we always use these symbols for containing elements of a set. So you want to use brackets like this. Okay, so this is common practice to use those braces here. Sometimes we write because let's say we're told that this is function f, and maybe there's a function g, a function h. If you want to specify that this is really the domain of that function, you could put dom subscript f. That's possible, and maybe just here range subscript f, or you could just put domain subscript f as well, maybe the full name. But you can put little f as a subscript to specify which function you're talking about. Otherwise, if it's clear from context, you can just put domain and range. Now, in another way to ask the same question would be, so this would be the same question as finding the domain and range of the following pair of coordinates. So if you've got 210, so that means to 2 you associate 10, 310, 420, 525, and 640. That's actually how this example is presented in the book, but I thought I'd start with a little diagram first. I think it's clearer this way. So the same answer would come out of this other question. Now let's try to take a look at what the domain and the range would be if we've got a formula. Okay, So this, for all the questions that come next, you're gonna find a range in the domain of the given function. So we start with this quadratic. Okay. Now to understand what the domain and the range is going to be, well, for the domain, it's actually pretty easy. Usually it's easier to figure out the domain than to figure out the range. The range could be tricky actually, or very difficult to get, but the domain is actually something that's pretty easy to answer. And so what's the domain? Well, look, what can I feed? What can I replace x by? That's basically the question you're asking yourself. So what can you feed into this function machine, right? So what can you replace x by? Well, you know, if we think about it, I could feed in 2, for example, that would work. I can feed in 3, that would work. I can feed in pi, that would work. Pretty much, there's no restriction here, okay? So it's pretty clear that x squared minus 1 can be evaluated, okay, no matter what the number is. Then maybe you're going to ask me like, well, is that going to be the case for every single function? Can we just replace x by anything? Well, we're going to just have to watch out for, okay, so this is coming up eventually, but for cases like this, if I've got square root of x, you cannot replace x by a negative because square root of a negative is not going to work. If you've got a fraction, watch out for division by 0. So if x is 1, that's not going to work. You're going to be dividing by 0. So mostly those are the cases we're going to have to watch out for. But if you've got a polynomial in particular, you can replace x by anything in a polynomial. So right away, we know the domain is going to be, so there are 2 possibilities. You can write it in interval notation like this, or maybe or you could just write what's easier here, just r, plain r. For the range, it's a bit more tricky. I would recommend at this point, so different ways of finding the range, but at this point, maybe rely on the graph of the function. So let's try to graph this function. It's a quadratic, so if we factor it, we can easily graph it. We see that 1 and minus 1 are the x-intercept. The y-intercept is minus 1, because if you replace x by 0, you get minus 1. And the vertex is halfway between the x-intercept, so it turns out to be your y-intercept as well. So your vertex is the y-intercept. So this is a function that looks like this. So for the range, we're looking at the possible. So remember that the range is going to appear on the y-axis. Okay, so your domain is the values of the x coordinates of the points that you have on your curve, and they lie basically like this is like the domain is like everything here. But the range, we see that we do not get values of y below minus 1, so that's going to be our range. Okay, so we see here that our range is actually going to be anything above minus 1. So next example, now we've got g of x, which is x plus 1 over 2 minus x. Okay, so once again you can look like, can I calculate g of 1? Yeah, you can do that. Okay, that would be 2 over 1, it would be 2. Can I calculate g of 0? Well, 0 plus 1 is 1, 2 minus 0 is 2, so that's going to be a half, so that works. So we see 1's in the domain, 0's in the domain. Can I do, I don't know, minus 1? Does that work? Can I replace by a negative? Minus 1 plus 1 over 2 minus minus 1. So that's 0 over 3. Yeah, that's okay. 0 over 3 is okay, because if you have nothing and you divided it into 3 equal parts each, nobody's going to get anything, okay? But one thing you cannot evaluate is something like 3 over 0, or anything over 0 is not going to work. And this is going to happen if you replace x by 2. So notice if you replace x by 2, you get, so this is undefined. You get 3 over 0. Okay, so 2 is not going to be part of the domain. So one thing is, we cannot divide by 0. So that means that, okay, So we're going to have to exclude values such that 2 minus x is 0. We cannot have this. So in this case, there's just one solution, but depending how complex your denominator is, you may have like more than one value of x to eliminate. So in your domain, so domain of G would be, or you could just put domain here, it's pretty clear. Domain is anything but 0. Okay, so how we're going to write this down? In interval notation, you can write this. This is anything but 0. Notice the open brackets, right? Because you don't want to include 0, right? You don't want to put something like this. If you went to French school and you were used to writing a bracket like that, that's fine too. You can do that. Okay, so you can write it like this if you prefer. This is acceptable. Actually, I really like this notation. I had to get used to the parentheses for open brackets going to English school. There's another way to write this down. You can also say this is all reals, but remove 2. So this is the operation for removing elements of a set. So this is all set of real numbers, but remove the number 2, so the set containing 2. So that's actually, I prefer that because this is shorter to write down. Okay, so this is your domain. What's the range? It's more tricky here, so we're not going to go in. We're not gonna find that one. So just write range more. So wait for calculus. Because here we're not going to be able, it's too tricky here, at least for the moment. Let's do another one. F of x is root of 7 minus 2x. So now we have got a square root. So as I told you, the other thing with finding domains, you cannot have a negative under the square root. So we cannot have a negative under the square root. So you can actually have 0 under the square root. Square root of 0 is 0 because 0 squares 0. So it's really negatives that you don't want. So exclude here. I'm going to exclude well, maybe values such that 7 minus 2x is negative. We don't want that. So here we have to solve this inequality. So you can actually see where solving inequalities is useful. So we have to exclude every x that's above 7/2. So that means our domain, so anything else is acceptable. So anything, so hang on, let's be careful. So this is the real line. Here's 7/2. We want to exclude those values. So we want to keep, so our domain is going to be here, okay? Including 7/2. Okay, so let's write that down. So it's going to be everything from minus infinity to 7/2 included. Now at 7/2, what happens is that the function value is 0, so you get 0 underneath the square root. And then after that, you can get any positive number, okay, by making x, if you decrease x, you're going to increase the value of the square root. So here's kind of easy to figure out the range. So the range would really be anything starting from 0, so what you get if you replace x by 7/2, and then all the way to infinity if you make x negative enough. So in fact, if we were to graph this function, it would start at 7/2, full dot there. 7/2 is at 7/2, it's defined. When x is 0, you see we'd get square root of 7. So with 0 square root of 7 is our y-intercept, and then it looks like this basically. It's like a, so if you remember your toolkit function, square roots will typically look like that. But if you figure out what the range is, the domain, and here actually the range, I'm pretty happy. Well, you don't have to necessarily know how to graph this. We're gonna see that a bit later in the course. And then finally, last example, I'm gonna combine everything we've done. I'm gonna put square root of 7 minus 2x and divide that by x minus 2. Okay, so we need to exclude the values of x where 7 minus 2x is negative, because we don't want a negative underneath the square root. We need to exclude what makes the denominator equal to 0. Okay, so here we need to exclude 2, and as we did before, we need to exclude values such that x is larger than x. So let's take a look on a real line. So on a real line, 7.5, this is 3.5. 2 would be somewhere here. So we need to exclude everything above 7.5, so we'd keep that, but we also need to exclude 2. So this would be it. Okay, so if we are going to not the domain but a range, the domain is going to be anything between minus infinity all the way up to 2, and then from 2 to 7.5 included. And an alternative to that would be, you could write everything from minus infinity to 7.5, but remove 2. This I like less, so I prefer personally this notation in this case. So that's it. And for the range, once again, when we've got a fraction, it makes things a little bit more complicated. I would say also wait for a calculus, but I would say even in calculus we don't actually look at my students would have a trouble finding the range for that. It would take, it's possible, but you need to be solid on algebra. But finding the domain, as you can see, is pretty easy.